to find all of the parts if only some of them are known. For example, in an earlier program, we learned that the sum of the angles in any triangle is a straight angle, or pi radians, no matter what shape the triangle has. Therefore, if you know two angles, you can calculate the third angle. If you know all three angles and nothing else, you know the shape of the triangle, but you don't know its size, so you can't determine the length of any side. In this program, we'll learn that if three parts are given, and at least one of them is a side, then we have enough information to find the remaining parts. There are four different cases to consider. What we know: angle, side, angle, side, angle, side, 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 angle, and side, side, side. The sine and cosine ratios provide the key that unlocks these problems. Remember this.
Okay, that's it. There's more, but it'll come later. Okay. So today we're going to talk a little about something usually you get kind of towards the beginning of a trigonometry class. We're going to talk about trigonometry, solving triangles. But I want to talk a little first about the basics here, and I want to remind everyone about some things they learn hopefully in your geometry class. Because one of the things we were doing in geometry is we would look at two triangles, and we would try and decide whether these triangles were congruent. Everyone knows that term, congruent. The geometric word we use to say they're the same, or they're equal, or they have equal sides and equal angles. And there were a number of theorems that we used to show this, and I just want to see, does anyone remember any of these theorems? They almost all, we refer to them all by some letters, usually 3 letters. It's not the Pythagorean theorem, no. Anyone recall any of these?
Yeah.
Are you talking about the side angle and all those?
And all those.
Oh, SSA, SSS, and SAS.
Oh, all right. Just one theorem per customer, all right? Which is your favorite?
SSS.
SSS, okay. For those of you who need a little reminder, SSS says if 3 sides of the triangle are equal in length, then the triangles are congruent. So if I know this side is equal to this side, and this side is equal to this side, this is a very common way of showing this in a diagram in geometry. We mark these in a similar way, and these 3 are the same. We know these 2 triangles are congruent. That's side, side, side. I'm not even going to write this down. You see SSS and side, side, side. Okay, somebody else, another one? Yes?
SAS.
SAS, okay, angle, side, which says if I know 2 sides and the included angle are congruent for 2 different triangles, I can say the triangles are congruent. All right, someone else?
Yes.
Another one of these?
AS?
Yes. Yeah, I react to raised hands really well. Yes, go ahead.
AAS.
AAS, angle, side. Now, that's fine. Usually we don't think of it that way for a particular reason. To begin with, if we have two angles, as the video just explained, we have the third angle. So this is more like AAAS, or as we usually write it, ASA. Nothing wrong with what you were getting at, but they're the same thing, right? As soon as we have two angles, we have the third, so we can arrange them however we want. So if I have two angles, angle 1 and angle 2, and a side, okay, we have a third congruency. All right, so that's number 1, number 2, number 3. All right, we're still missing something here.
3 angles? 3 angles?
Okay, so if you have 3 angles, or if you have 2 angles, which is the same, it's not a, you don't have congruent triangles, you know something else about them. Anyone remember?
They are what? They are similar?
You have similarity, that's a similarity theorem, right? And we're not interested in that today, not yet. Okay, a hint, the fourth one has letters, it only has 2 letters, and they're different letters. Okay, does anyone recall HL? This is rather specific. It says if I have a right triangle and a hypotenuse and a leg are congruent, then I know those 2 right triangles are congruent.
But they just simply fit to SAS, right?
Yeah.
Sorry?
This case just simply fit to SAS.
No, it doesn't.
No.
Well, we know in angle, we know to size.
Because the angle is not, we don't know this angle here.
Okay. Okay.
This is actually very different. And let's just, for the sake of argument, we'll write this in the right order. We'll call it SSA for a right angle. Okay, I want to say some more about this, but first I want to say something in general. So I have these theorems that say if 2 triangles meet these criteria, they're congruent. Well, if 2 triangles meet this, or 3, or 4, or 5, or 6, or a million, they're all congruent. They all have equal parts. So what does that tell us about knowing these features of a triangle? It tells us that, for example, if I know 3 sides to a triangle, that triangle is determined. It's completely, when you use this term, it's determined. In other words, you can't have 2 triangles where you know the 3 sides, but they're different, right? They have different angles or whatever else is missing. Likewise, with these other theorems, SAS, if you have 2 sides and an angle, the triangle is determined. You can't have any other triangle. And likewise for ASA or hypotenuse leg. Now, in the case of, slightly more general case of side-side angle, we don't have the triangle completely determined. We have it mostly determined, though. And let me show you what I mean by that. Let's say I have a triangle, and I know, and I'm going to use a new sheet because I want to draw this nice. I know a side, and I know, just gonna kind of dot this in here, I don't know how long this is, I know an angle, and I know another side, okay? So you would think there's just one possible triangle there, but actually there isn't in this case, because I don't know which of these two triangles, let's A, B, C, and D. If I just know length 1 and length 2 in this angle, there are two possible triangles. There's A, B, C, and there's also A, B, D. Triangle A, B, D. In one case, this angle here, this unknown angle, could be an obtuse angle, or it could be an acute angle. So while in geometry we don't talk about SSA, in this class we're going to think of it as kind of an almost theorem. We haven't completely determined the triangle, but we've got it down to 2, right? Now maybe our problem will give us more information. If, for example, I give you 2 sides and an angle not included, but I say, and I want an acute triangle, then it is fully determined. Okay, so the point of all this is that when we have this limited information about a triangle, typically 3 items, we can determine, we know that the triangle is determined, but now with trigonometry, we not only know it's determined, we can find the missing pieces, the missing angles, and the missing sides. So that's what we're going to talk about today, or we're going to start talking about today. So let's start with a fairly simple example here. I have a right triangle, and I know 2 sides. I know the hypotenuse and a leg. I'm missing 3 pieces. I'm missing the other leg, and I'm missing 2 angles. Now, to find the third side, we're going to go back even a little further, and a lot, if you remember what you were saying before, if you can repeat it. Pythagorean theorem, right? That's pretty easy. Right? So what does the Pythagorean theorem tell me this third side is?
2, 3.
Oh, okay, good. This is a good triangle to remember for the SATs, which, if any of you still need to take that. Yes?
No mind, I just.
3, 4, 5, right triangle, right? Or, if the numbers aren't so nice, we can see that 5 squared equals 4 squared plus x squared, this is x, or x is the square root of 25 minus 16, which of course is square root of 9, or 3. All right, so that's pretty easy. Now we have to go lean back on our trigonometry to find the angles. Right? As it turns out, we've got a cornucopia of routes to finding this, because we have 3 sides of the triangle. We could use any of our inverse functions we want. Any of the 6 inverse functions that we've looked at would allow us to find these angles. But let's do this simply here. Let's just take a look at this angle here. We know that, for example, the sine of this angle is what? It's the opposite over the adjacent. So the sine of, say, theta is 4 over 5. Or the inverse sine of 4 over 5 is the angle. Similarly, we could have used 3 over 5 as the cosine of this angle. And we could have used found the inverse cosine of 3/5. Similarly, we could use the tangent. The tangent is the opposite over the adjacent. So the tangent is 4 over 3. So we could use the inverse tangent function. Now, I don't know why you would want to use the inverse cotangent, inverse secant, or inverse cosecant in this case. It would just be a little more complicated. But you could. Okay, so that's one very simple problem. I guess, did I get all my calculators back?
I think I have 2 here. I think I'm owed 2 calculators, so.
Thank you, that's one. For the, oh, I really hope I don't lose a calculator.
I gave mine back.
Thank you. I'm missing, let's see, it's a TI-83 plus, if you know.
Over here by your computer.
There we go, thank you. Okay. All right, so let's use the 83 plus. As always, check the mode. I'd like to get my result in degrees. And which shall we use? Let's start with the one I started with.
It's 53.
Take the inverse sine of 4 over 5. And we get 53.13 degrees, approximately. So at this point, now you have a choice. You can find the third angle by
90 minus the angle.
by noticing that the angles in a right triangle are complementary, yes. Use the fact that they add up to 180 and come to the same conclusion, or you could use another trig inverse function. Okay. Here's a more general triangle. This fits under the category of SAS, right? We know it's determined, but how can we figure this triangle out? Well, I'm just going to go through it. In this particular case, we can drop an altitude here. And I've used a nice, easy, doesn't look right.
That's fine.
No, it doesn't. That looks like this. That's the 60-degree angle. Sorry. This is the 30-degree angle, right? I've given you a nice, easy angle here that we don't have to use the calculator for. If we did, you could still do it. So we know this is a right angle. So the question is, what is the base and what is this other leg here? Well, this leg, of course, is 4. We could have found that by using one of the trig functions. We can see that this value, x over 8, has to be what trig function of 60 degrees? Cosine, right? Okay, and then we know that the altitude is just 4 times the square root of 3. All right, we're partway there. Wait a minute. We know that the total side is 10. So if this is 4, this has to be 6. Right? So now, again, we have side, angle, side, and we know this triangle is determined. How are we going to find this other side here? Pythagorean theorem, right? So we're going to take the square root of 4 times the square root of 3 squared, which is 16 times 3, or 48, plus 36. That's the square root of 84. All right, and now we're back to using inverse trig functions here. We know that 6 over the square root of 84 is what trig function for this angle? Cosine. Did I hear cosine? Cosine of x, whatever that angle is. So now we just use our inverse trig function, right? Cosine inverse. Oh, thank you. 6 over 84. I don't know what that's about. Let's take a look.
49.
I believe you. I'm just. 49.1, all right? And again, we have another angle to figure out, but that's just going to be the complement of this angle. And that angle plus 30 degrees will tell me the final angle.
40.
Okay. All right, so this is another example that we're prepared. Here I have the whole thing written out for you, if you like. And I don't have it all written out, but I still have the wrong angle here. Okay. That's most of today. I have a few more things to say. And then we'll get to work on something. I want you to think for a second. If I have an angle, and I'll just make up some numbers here. Let's say 40 degrees, and this is 10, and this is 7. What can we do with this? Well, we drop an altitude, but we don't really know where it drops to, right? So that doesn't really help much. We can't use the Pythagorean theorem, right? Because we don't have a right triangle. We're a little stuck right now. We're not going to solve this today. We're going to solve this on Wednesday or following Monday. But we need more equipment. We need more theorems to figure this out. So that's one thing I wanted to talk about. I wanted to mention we have somewhere to go with this triangle stuff, because before we're done, you're going to know how to solve any determined triangle. The other thing I wanted to mention, so that you are not confused by any of the homework, because I think you may run into this in the homework. Homework defines the book defines two terms which I'm not really all that thrilled about. Because to me they're not really part of math, they're more kind of part of surveying or engineering. But I don't want to leave you here trying to do the homework without these. The first is the angle of elevation. And what that refers to is if you have some kind of horizontal line here, and then you pick some angle above that, that's an angle of elevation. That's pretty simple. Likewise, we have an angle of depression. And similarly, if you have a horizontal line and an angle pointing down below it, that's an angle of depression. The only application for this that I really like is if you start to learn how to do celestial navigation. If you're a celestial navigator, you have an interesting little device. If you get out there at dawn or sundown, and you kind of look at the horizon with one little telescope, and you look at a telescope, a pointer, and another at a star, and you measure the angle of elevation of that star. You do that for a couple stars, you can figure out where you are in the world. So, but we're not going to do celestial navigation, not today anyway. All right, I have a handout that has some practice problems, and I guess we'll just pass it that way. Pass that straight back. And I think you're going to find these problems pretty straightforward, pretty simple. And we'll see if we have time to go over a few of them. Any extras? There you go. You need one, right? All right.
7 to 2 7 hours or 6 hours? Actually 7 to 8.
I apologize if this feels too much like another quiz after the quiz.
Too soon.
Too soon, yeah. Thank you.
So do we have a quiz soon? A midterm soon?
The midterm will be 2 weeks from today.
Okay.
I will have more to say about that later in the week. These quarters, they run really fast, don't they?
Yeah.
Is number 5 still a right triangle?
Hmm?
Is number 5 still a right triangle?
Oh, yeah, I guess I should have made that clearer. Number 5 is a right triangle. Number 7 and 8, if you get that far, are for people with more, what's the right word? Love of mathematics. Yeah. You actually have to work a little to find the solution. Let's start off with the first page. Yes. Oh, you want to borrow a calculator? All right, sure. Yes. Yes. Yeah.
Oh,
On the other page, all the angles, you guys, you're gonna be mathematicians if you're gonna be that picky, yeah. Assume all the angles that look like right angles are right angles.
I was looking at them. Yeah, I'm like.
Hmm?
The first one. This the triangle you do.
Actually, you don't have to assume it, if the directions say, for these right triangles, okay.
There you go.
I think I'm tempted to show you, I use this really nice program called Geometer Sketchpad whenever I'm doing these little diagrams. And some things it does really, can everybody see that? Some things it, let's see, I have to hide my email. Some things it does really nicely. So, for example, if I want a right triangle, pick a line segment, and there's a line segment. I guess I should make these all nice and thick so you can see them. Oops. And you say, okay, I want to construct a perpendicular to this point in this line. So say construct that perpendicular. And now it's really easy to say, okay, I want to have a triangle. Construct my triangle. Now I hide my line because I don't really want you to see that. And now no matter what I do to this, it's going to be a right triangle. So that's the easy part. If I want to actually do the little symbol that shows you it's a right triangle, and I want to do it the right way, I have to draw a little circle here. And I have to draw a little circle here. They should have like a function to do this. And I have to draw a perpendicular here. And I have to draw. I just want to show you why I didn't bother doing this for this worksheet. I'm lazy. And I have to draw another one there. Put in a point here. Now I hide all these guys. No, too much. Has a really good undo. Undo it, undo whatever you just did like that. Show the circle. Okay, that took all that work just for that little guy. Do it right. I don't like points. Ah, we got a nice red triangle. Yes?
Is there a button that makes it square?
No. That would be nice. They do have a button though that you can say, animate point.
No, just make sure.
Now, just do that for a while. Okay. Anyway. I know that was really fun. Oh, there's something else it'll do too, which is kind of nice. If I say, let's see, there, points back. I'm sorry? Oh. If I, have to do this the right way. I were to then, even put labels on it. So that's A, B, C, so if I then say like A, C, E, measure angle, and then I can calculate see, I think I can oh, maybe I don't know how to do it. I think I can put these measures in and show that they always add up to 90 degrees, but I can't figure out how to do that. So another time. Yeah, if you ever like want to teach high school geometry or college, or you just are really curious about fooling around with geometry, it's a really neat program. To some degree, it deals in absolutes of the sort. Kind of knows that, you know, the angles don't add up to approximately 180, they add up to exactly 180. Okay. Let's see here. Angle A and C, that's usually the hypotenuse. This is 23. Does anyone have some answers for the missing parts? Okay.
The B,
Angle B,
yeah, will be 67.
67 degrees, okay. So what about the other two sides?
The side close to 67 is 10.55,
55,
and that one is 24.85.
24.85, yeah. Obviously, my diagram is wrong,
Yeah.
but out of proportion, but that's okay. Right,
Do you know the answers, or you will just believe them?
I'm taking your word for it. I'm assuming the other students will complain if they don't like your answer. Or they'll keep quiet.
I got the same.
I don't believe you.
Huh?
I don't believe you.
He's a skeptic. Okay, let's see. Number 2 is kind of the same problem, so I'm going to skip over that for now. I'll post the answers online tonight or tomorrow. Let's look at 3. That's a little different. A is 428, and B is 797. Okay, so really want a calculator for this one, right? What am I doing here? Pythagorean theorem, 428 squared. Yeah, I'm just going to mention this in case somebody hasn't noticed. This particular calculator, it's a 48. But the fact that it's a 48 doesn't mean it does this necessarily. I have a 48 that does plus that doesn't do this. But you notice it's like the cursor is still up on the exponent. So some of them do this and some of them I don't understand. Just be careful when you're typing something in that it's what you expected. Okay, so it says it's 904.65. And let's look at this angle here, 797 divided by that answer. What function is that? Cosine, okay, so inverse cosine of, oh, I didn't check my mode. Yeah, it's okay. Inverse cosine of the answer, no, that didn't work. Inverse cosine, answer 28 degrees, 28.23 degrees. Right, and problem 4 is similar. Everyone get those numbers more or less? Okay. All right. These look like the same problems, so I'm just gonna let you check the answers. Anyone attempt number 7? Okay. Over one hand. Okay. Anyone have any ideas, except for you? Did you get the answer?
Yeah.
Okay. So what we're saying here is this is a 45-degree angle. This is a right angle. So this has to be what? 45. And we know that area 1 is, well, 1.5 times area 1 is area 2. So we want to find those missing angles. Doesn't seem like we have enough information, does it? We don't know anything about the sides. Well, we know hardly anything about the sides. What about this, this distance here versus this distance here?
1.5.
Yeah, let's call this length B. This is 1.5B, right? Do we know anything about this length here from, call this, I don't know,
It's equal to B.
we'll call this length C. I should have called it B for base, but I didn't. What do we know about C?
Equal to B.
It's equal to B, right? Someone else tell me why it's B and C have to be equal.
Because it's 45 degrees on the both sides.
Okay. That would be good enough for me, but I want a theorem. What's the theorem that tells me that if these angles are the same, these sides are the same? No. What kind of triangle is this? Aside from being right, it's an isosceles triangle, right? Everyone remember that one? We have an isosceles triangle. Well, these sides are equal, and the opposite angles are equal. The opposite angles are equal. The opposite sides are equal. Okay. So we know this is B. So okay, we're getting there. Stare at that for a second. What about that diagram? We know this is B, this is 1.5B. We want to know these two angles, and we want to know this side.
We can find side. We can find side.
Yeah, actually, we don't care about the side, because it doesn't ask for it, but sure.
Okay.
How can we, what is this side here?
Find b squared plus 1.5 b squared square root of
Square root, Pythagorean theorem. Okay. But we don't want it to get too messy. What are we going to use knowing these two sides to find these angles?
Can't you just multiply 45 by 1.5?
Sorry?
Can't you just multiply the 45 degrees by 1.5?
Okay, and which theorem tells you that?
I don't know which theorem it is.
No. Good, because
But-
there isn't a theorem. Isn't that right? I mean, it's not. I mean, there's something else here you know, right? For this angle, right, there's some trig function that you can, you know one of its trig functions, right? At least one. use the, you know, the hypotenuse, this is the hypotenuse, you know that, but that's an ugly number. This is a nice number. What's the trig function I'm looking for here? Tangent, right. Says the sine over the cosine is the tangent. I'm sorry, the opposite over the adjacent is the tangent. So what's the opposite over the adjacent?
E over 1.5.
It's 1 over 1.5 or 2/3, right? That's the tangent. Let's use our magic calculator here. What's the inverse tangent of 1/3? Okay, there it is. Now we have that angle. Is that what you got me?
You said 2/3, right?
Actually, no. It's 33 degrees because you.
Because
you found it, yeah.
you're right.
Yeah.
Thank you. Who pointed it out? Okay. 2 divided by 3. Thank you. Is
Yeah,
that better?
33. Yeah.
Okay, all right. All right. I think today has been exhausting enough. If you're interested in number 8, which is harder, you can stick around. Otherwise, like I say, I'll post these in the next day or two, and we'll take a look at the quiz on Wednesday. Otherwise, clear on it.
So the midterm is not yet, right? I guess it's in 2 weeks. Every 2 weeks we have music.
If you want.